Engineers create things and they build them using materials. These materials must handle mechanical loads, conduct or insulate heat and electricity, allow or block magnetic fields, transmit or reflect light, and withstand harsh environments. And they must do all of this without harming the environment or becoming too expensive. And then there is a crucial partner in all of this, the process. To shape material into something useful, you need the right method. Not just any process, but the one that works well with the chosen material. Sometimes it's the process that leads, and the material must be selected to match it. Humans have been using materials for over 10,000 years, yet nearly all the materials we rely on today were developed within the last century. And the number is staggering. Modern engineers have access to over 160,000 different materials. With growing demands for higher performance, lower cost, greater efficiency, and minimal environmental impact, choosing the right material has never been more critical. It's all about the properties that decide the material selection. So, what exactly are these properties? Some, like density and cost, are fairly well known, but many others are less familiar, and understanding them clearly is crucial. Let's start with one of the most important groups, mechanical properties. Those that determine how well a material can carry a load safely and reliably. Take a steel ruler for example. It bends easily but springs back when released. That's what we call elastic behavior. The stiffness during bending depends partly on the shape of ruler. A thin strip bends more easily, and partly on fundamental properties of material itself, the elastic modulus. Material with high elastic modulus like steel are naturally stiff. Those with low elastic modulus like polyethylene are much more flexible. A steel ruler bends elastically, but if it's a good one, it's difficult to bend it permanently. That's because permanent deformation relates to strength, not stiffness. The ease with which a ruler can be bent and stay bent depends not just on its shape, but on another key material property, yield strength. Material with high yield strength, like titanium alloys, are hard to deform permanently, even if they aren't particularly stiff. On the other hand, material like lead with low yield strength deform easily. As metals deform, they often become stronger, a phenomenon known as work hardening. But there is a limit, the tensile strength. Go beyond that and the material fails. The amount a material stretches before breaking is known as its ductility. Now imagine the ruler is made from glass or plexiglass, as many transparent rulers are. You can't permanently bend those, they simply crack or break. This is where fracture toughness comes in. It measures a material's resistance to crack propagation. Most steels are tough and have high fracture toughness, but they can be made brittle. Glass, by contrast, is the classic brittle material. It has very low fracture toughness. Now let's talk about thermal properties. As temperature rises, the material's behavior changes. Its strength decreases, it may begin to creep, that is, slowly deform over time, and it can oxidize, degrade, or even decompose. That's why every material has a limit known as the maximum service temperature, the highest temperature at which it can function reliably. For example, stainless steel has high maximum service temperature and can perform well up to around 800 degrees centigrade. In contrast, most polymers have much lower maximum service temperature values and are rarely used above 150 degrees centigrade. Choosing material with the right thermal properties is critical, especially in high temperature environments like engines or turbines. Some materials like metals feel cold when we touch, while others like wood feel warm. This sensation is linked to two key thermal properties: thermal conductivity and heat capacity. Materials with high thermal conductivity are ideal for transferring heat efficiently. That's why they are used in cooking pans, radiator, and heat exchangers. On the other hand, materials with low thermal conductivity are just as important. They act as insulator, keep home warm, reducing energy use in refrigerators and freezers, and protecting spacecraft from the intense heat during atmospheric re-entry. When it comes to electrical properties, the most fundamental are electrical conductivity and insulation. Without conductive materials, we wouldn't have the convenience access to light, power, heating, control systems, and communication that we now take for granted. Metals are excellent conductors, especially copper and aluminum, which offer a balance of high conductivity and affordability. But conduction isn't always desirable. In components like fuse boxes, switch casing, and power line supports, we need insulators, a material that don't conduct electricity but can still bear load, tolerate heat, and withstand electrical sparks. Here the key property is electrical resistivity, which is the inverse of conductivity. Plastics and glass typically have high resistivity, making them ideal insulators. Interestingly, with certain treatments, even these materials can be made to conduct slightly when needed. Electric currents create magnetic fields, and moving magnet can generate electric current in nearby conductors. While most materials respond very weakly to magnetic fields, a special few known as ferromagnets and ferrimagnets can retain a magnetic field. These are called hard magnetic materials because once magnetized, they are difficult to demagnetize. They are used in permanent magnets found in headphones, motors, and dynamos. The key property here is remanence, which measures how much magnetism the material retains. On the other hand, soft magnetic materials are easy to magnetize and just as easy to demagnetize. These are used in applications like transformer cores and deflection coil of old tubes. A component's performance is directly limited by the properties of the material it's made from. To meet a specific performance goal, certain design limiting properties must reach minimum target values. If a material falls short of this, it simply isn't suitable. The right material is selected because it not only meets this performance target but is also compatible with the manufacturing process needed to shape, join, and finish the final product. Material must meet mechanical, thermal, electrical, and magnetic needs while staying cost effective and eco-friendly. Choosing the right one ensures performance and process compatibility. With over 160,000 options, smart selection is a key to good design. Now you know about the basics of material properties. We will learn about every property in detail in future videos. With that, if you are curious about something, comment below or email us. Subscribe to Material Engineer to deep dive into the world of material science. Hit the bell icon so you will never miss an update. Until then, keep learning, keep asking, and keep exploring.